Hi guys, Miss Ellery again. This is part 3 of our non-standard cell notes, and in this part we're going to talk about how we can use standard cell potential to calculate delta G, free energy. So in order to do that, we're going to use this equation here. So delta G, free energy, is equal to negative NFE. So what do all of those letters mean? N is the number of moles of electrons that are transferred. F is Faraday's constant, which is 96,485. We've used this value before, and so now we're going to use it in the context of our electrochemical cell. E naught, which is our standard reduction potential that we've been calculating for our galvanic cells. And then delta G is our standard free energy. Throwing it way back, remember that if you get a negative delta G, that means that the reaction is spontaneous, otherwise known as thermodynamically favored. And what that means is that in this situation, the reaction is going to naturally progress in the forward direction from the reactants to the products. So we're favoring the products. This would be the situation of a galvanic cell, where the electrons spontaneously flow from the anode to the cathode. When we get a positive delta G, that means the forward reaction is non-spontaneous. It's not thermodynamically favored. So those electrons are not going to be flowing from the anode to the cathode as they would normally. And in this situation, we're actually going to favor the reverse reaction. And so the electrons are going to flow from the cathode to the anode. And that is going to be driven by the use of an electrical source. So you actually connect a battery to those scenarios and cause the electrons to flow backward. And that's used to do something called electroplating. So the relationship between free energy and E, we can also take this equation and we can combine it with another free energy equation. So we learned, again, way long time ago, that delta G is equal to negative RT ln K. And we can set these two equations equal to one another because they both equal the standard free energy of the system. And therefore, if you know E cell, you can also figure out your K value. And so we can rearrange the equation using a little bit of algebra. And we get our E cell is equal to RT over NF. And so because this is under standard conditions, we know our T value is 298. We know our R value because that's a constant. We know our F value because that's also a constant. So we can simplify these down. So R times T divided by F will give us this number, 0.0257 over N times ln of K. So this is another equation that would be on your AP equation sheet. So now if you know standard cell potential, you can actually solve for the equilibrium constant for that particular reaction. So here's some things to know. Let's evaluate our constant K, our standard cell potential, and our free energy. So if we look here, if we have a positive E cell and we have a negative free energy, that means that we are thermodynamically favored the going from the reactants to the products. So this is going to be a spontaneous reaction. So think galvanic cell. Those electrons are going to flow from the anode to the cathode, and the forward reaction is going to be favored. If E cell is 0, that means that we've reached equilibrium, right? K is equal to 1. And if we're at equilibrium, this would be a scenario where we would have a dead battery. And then finally, if we end up with a K value that is less than 1, where we have a negative E cell and a positive delta G, this means that the forward reaction is not favorable whatsoever. So the forward reaction is not thermodynamically favored. Those electrons are actually going to be moving in the opposite direction. This would mean that the reverse direction would be favored, so the flow of electrons from the cathode back to the anode. All right, so let's do an example problem dealing with our new equation. So it says find the delta G and the equilibrium constant for the following reaction. So the first thing that we need to do for this is we're going to have to figure out what our delta G happens to be. So in order to do that, we're going to use our standard cell potentials to make that calculation happen. So we're going to use our equation delta G is equal to NFE, and I'm going to rearrange this so that we end up with a positive cell potential. So to do that, I'm looking at these two values. I'm going to need to reverse this reduction potential to make it an oxidation potential, which would be positive 1.8 or 1.18. I'm going to leave my other one as reduction, because when I add these together, I'm going to end up with an overall positive E cell. The other thing that I need to do is I need to make sure that my electrons are going to cancel. So here I have 3 electrons on the reactant side. Here I have 2 electrons on the product side. So I'm going to need to multiply this by a coefficient of 2. I'm going to need to multiply the bottom by a coefficient of 3. So the overall equation is now going to have 6 electrons on each side of the equation. So when I go to plug this into my delta G is equal to NFE, delta G is equal to -6, and that 6 comes from our 6 electrons, times Faraday's constant, and then times our E cell, which was 0.44 volts. So once I've done that, then I know that my delta G is -254,719 joules, which is the same thing as roughly -250 kilojoules. There was another part to this question. So in addition to finding our delta G, which we came up with as -250 kilojoules, we also need to find the K value. So taking a look here, we're going to use our standard cell potential from before. And this time we're going to use the equation that our standard cell potential is equal to 0.0257 over N times ln K. So I'm going to take my standard cell potential, which is 0.44. I'm going to set it equal to my 0.0257 over 6, because I knew that I had 6 moles of electrons, and times ln of K. So next I'm going to simplify. And so when I take my 0.0257 divided by 6, I get this value here. Then I'm going to divide both sides by this value so that it cancels on this side. And when I do that, I end up with 102.73 is equal to ln of K. Now to undo this and to solve for K, I'm going to use E. So E raised to the 102.73 and E raised to the ln of K. That will cancel my natural log of K and leave me with just K. And E raised to that, I get my K value is equal to 4.63.